humans, we make decisions all the time. And I'm pretty sure that you will agree with me that these decisions are sometimes influenced by cognition and sometimes influenced by internal biases. So what I mean by cognition is like computations of things like expected reward, variance of the reward. By internal biases, what I mean is our internal preferences, our emotion, our mood. And so actually, it's known since a long time, and the very first models of decision-making were viewing these two components as two antagonistic forces that were driving decisions in opposite directions. However, more recently, it has been shown through case studies that cognition and emotion both are needed in order to make decisions. And yeah. Is it better? Yeah. Okay. So both cognition and internal biases, it has been shown that both are needed in order to help us make decisions. And in particular, I mean, the idea that emotion plays a modulatory role on whatever cognition is telling us to do. So, but the exact relationship between the two is not very well understood. And so in this study, we wanted to try to answer two very simple questions. The first one is, how do cognition and internal biases integrate? And the second question is, where is this happening in the brain? So of course, we are not the first to try to answer these two questions. And if you look at the literature, we'll find a zoo of studies, but they will mainly fall into three types of categories. The first type is about animal studies. So typically primates, but also some studies in rodents. But the difficulties with primates and with animal studies is the translation to human. Right? Then when you focus on human studies, the first type is lesion studies. But with lesion studies, essentially you have no neural data. You just know that one piece of the brain is missing, and then you can try to infer a relationship between that fact and some behavior. And then the vast majority of human decision-making studies is using fMRI. The big disadvantage of fMRI in the context of decision-making is the temporal resolution of fMRI. So fMRI, typically we have one image every second, every 2 seconds. But we know that decision-making is much quicker than that. And so if we want to be able to track the neural dynamics at the time scale that matters for decision-making, we need something else. And also if we want to look at neural rhythms, then we need something else. And at Johns Hopkins University, in collaboration with my PI and with also clinicians at the Cleveland Clinic, we were in this unique position with a unique opportunity to use a quite new technology that is called stereotactic EEG that I will describe later. But the idea is that this new technology fulfills all the requirements that you would wish for an ideal study on human decision-making. So before getting into the details, I would like to give you an overview of the approach. So essentially, we will have some subject that will be playing a gambling task with us. And at the same time, we will record from their brain. And to try to answer the first question, how do cognition and internal biases integrate, the approach we took is a modeling approach. So essentially, we will try to model their behavior using input-output system, but also with some internal state, so a state that evolves at each trial and that might bias the decision. So from the observation that we will make, we will try to estimate the model parameters, but also this internal state that we cannot observe in the experiment. Then in terms of trying to answer the second question, we use a very standard spectral analysis. But the key is that we try to gain from the knowledge we had during the modeling process. And the idea is that we will try to identify in this huge neural database the few components that we identify as important in the model. So the outline of the talk is the following. I will first describe the data, so both the behavior and the neural data that we have. And then I will try to tell you about how we try to answer these two questions that I'm interested in. So let's have a look at the data. So we are recording from a small population of epileptic patients. And these patients are drug resistant. So it means that the doctors have tried to use different drugs to help them. and apparently none of them was sufficient to help them. So one of the last solutions for this type of patient is to go under surgery and to have the focus of their epilepsy, so the part of the brain that is responsible for the generation of these epileptic seizures, and to remove that part of the brain. So of course, before doing that, the neurosurgeon would like to identify what's this, as closely as possible, what is this part of the brain. And usually to do that, what they used to do, and what is still done in a lot of cases, is what is called ECOG. So the idea is that you open the skull, and then you place a grid of electrode on the surface of the brain, and then you record the activity from the surface. However, at Cleveland Clinic, they are doing something else. So our collaborator, Jorge Gonçalves, was trained in France, where this technique was developed, and he was the first to bring back this technology in the US at Cleveland. And so the idea of this technology is that you just need to drill some holes in the skull and then insert depth electrodes. Okay? So on the image on the left, you can see the side face of a patient, and you see that you have about 14 bolts, and each of these bolts is a different electrode that is inserted in that patient's head. And then on the image on the right, you see a bunch of wires, but you also see lines. Each of these lines is a different electrode, and each black dot on each line is a different contact on that electrode. So you can imagine that we are recording from a large number of locations in the brain. Okay? So the advantage is that we get cortical but also subcortical recording at a very fine temporal resolution, and the type of activity that we record is local field potential. And then we ask these patients to play a simple game with us. So it's a game of cards, and the goal of the game is to get a higher card than the computer. Okay? But we tell the patient that they will play with a very simplified deck of only 5 possible cards: 2, 4, 6, 8, and 10. And we also tell the patient that the deck is infinite. So essentially, each time a card is thrown from that deck, there is an equal probability of receiving one of these 5 possibilities. Okay? Then the patient will have to place a bet, so that's the decision. He will have to decide if he plays $5 or $20 on the fact that his card will be higher than the computer card. Okay? So if the patient win or lose, then he will win or lose the money that he bet. And if it's a tie, then there is no gain, no loss. And as a side note, we play with virtual money because we are not allowed to play with actual money with these patients. Okay, so the task goes as follows. There is first a fixation point where the patient has to move a manipulendum. So that's how the patient communicates with the computer, and to move a cursor to that fixation target in order to make sure that the patient is paying attention to the task. Okay? Then the patient card is shown. Okay, so in this case, a 6. And so again, it's coming from one of these 5 possibilities. The computer card is hidden, again, also coming from one of these 5 possibilities. Then the patient has to move the manipulendum in order to go to one of these 2 targets, either the $5 target or the $20 target. And so the decision is, I will bet $5, for example, on the fact that my card will be higher than the computer card. Then after some small delay, we show the computer card, in this case a 2. The patient realizes that he won, and we indicate that to the patient with some text and also with a picture of money that seems to be rewarding. Okay, so there is a very simple strategy if you want to play that game and to try to maximize your expected reward. So for example, if you are dealt a 2 or a 4 and you have to bet $5 or $20 on the fact that your card, the 2 or the 4, is higher than the computer card, what would you do? Would you bet $5 or $20? Anyone? 5, right? I mean, you have less chance to win, so you should bet low. Similarly, if you are dealt an 8 or a 10, then I guess you would bet high, right? You have a good chance to win, so you should bet high. However, what would you do on a 6 card? Yeah?
What if you did the last time you got a 6 card, if you won?
Okay. That's good. So, I mean, some people might think about just, flipping a count. Some people might take into account what they have in memory, some kind of internal state that evolves as a function of the game. And so that was also actually our hypothesis, that something else needs to be driving the decision. So, but let's have a look at what the patients are doing. So here on the horizontal axis, I'm showing the different card value. the vertical axis is showing you the proportion of high bets on each of these 5 cards. And so each dot is a different patient within each card. Okay? So you see that most of the time on 2 and 4 they bet low, most of the time on 8 and 10 they bet high, and on the 6th card you have more variability. Okay? But you see that in average they bet more often low than high. The reason why we think they do that is because the variance of the reward is higher when you bet high than when you bet low. And so if people try to minimize the risk, so minimize the variance, they might be betting low more often than high. So we can also look at the reaction time, so the time the patient takes to respond. And we see that we have this very nice bell shape where we see that for 2 and 10, they respond very quickly, while for the 6th card, where it's like more ambiguous, then they take more time in order to make their decisions. Okay, so then we wanted to be able to explain this data. And so we want to be able to explain both the across subject variability, so we see that all subjects are not doing the same thing, but we also wanted to be able to explain the across trial variability. So within the same subject, why sometimes a subject is betting high on a 6 and sometimes low on a 6. And also why sometimes does a subject bet high on a 2. So we see that some subjects do that. Doesn't make a lot of sense because there is no chance to win. The best you can do is tie, but some people do that. But we wanted to be able to explain that. So as I told you, the approach we took is to try to model their behavior. So the output that we observe is the decision. So it's a binary decision that we model as a binary random variable coming out of a Bernoulli process. So you can think of it as just a coin flip. But the coin might be biased with a probability P of high bet. Okay? So if P is equal to 0.5, then it's a fair coin. If it's higher than 0.5, then you have a greater chance to bet. You are biased to high bet. If it's lower than 0.5, you are biased toward low bet. Okay? And then we say that this probability P is influenced by 2 types of information. We have cognitive inputs that can be computed directly from the card that the patient is observing. And we have also internal bias state that is essentially coming from some kind of internal dynamical process that is essentially generating a new state at each trial. So you have this trial that is updated at each state that is updated at each trial. And of course, we have different type of information that can influence this internal state. So we have the player card, the computer card, but also we have some feedback because we know that the outcome of our decision might influence our internal state. So that's why we have the feedback there. So in terms of equations, we have the following. So we have the probability of high bet, which is P, and then we say that this probability through this log function, which is just the log of the ratio of the odds, which is very standard in this type of modeling, is influenced by 3 terms. We have a notion of return, which is essentially just the expected outcome. We have a notion of risk, which is the variance of the outcome. And then we have this notion of internal bias, which is the state of the system. Okay? So now the next thing I need to tell you is how is this state evolving. Okay? So that's the state evolution equation. And so we decided to use, again, a very simple model. And so let's think about the state as emotion for the sake of the explanation of this equation. So this equation, what this equation tells us is that my emotion at the next trial will depend on my current emotion. So that's some kind of memory. But it will also depend on some inputs. And so we have a first input that is just the card value. So if you receive a 10, you might feel lucky, you might feel good. If you receive a 2, you might feel bad. And then we have a second input, which is the feedback, so essentially how you perform. And we use just the reward prediction error. So this is very standard. It's just the difference between the actual reward minus the expected reward given your card value and the decision you took. Okay? So that's the full model, quite simple, but we have few unknowns here. So the only thing we observe are the input and the outputs. Okay? So the model's parameters are unknown and also the state are unknowns. So we use some very standard maximum likelihood estimation technique in order to estimate both the parameter state, the parameter of the model, and also the state. Okay? So we use some expectation maximization algorithm in order to solve this maximum likelihood problem. I would like to show you some results. So here I'm showing you the result of the modeling for one particular patient. Okay, so this is F316, and we see that each dot in that diagram corresponds to one particular trial. On the horizontal axis, you have the internal state for that trial. On the vertical axis, you have the probability of high bet for that trial. Okay? And the different symbol correspond to different cards that the patient receives. So we have all the 2 cards, the 4, 6, 8, and 10. Okay? So the different curves that you can see are coming from the model, right? I mean, these are coming from the structure of the model. But we wanted to be able to overlay the data to the modeling result. And so the way we overlay the data is by coloring these symbols. So each time you see blue, it means that the patient actually places a low bet on that trial. Each time it's in red, the patient actually places a high bet on that trial. And what we see is that most of the blue is toward the low probability of high bet, most of the red toward a high probability of high bet. And we also see that, for example, you have few trials where the patient had 2 cards, so these lower triangles, but the patient actually decided to bet high, so these red lower triangles. And what the model tried to do in order to explain this is to associate a high internal state to these particular trials. So to explain the bias toward a high bet. Similarly, we have few trials where the patient actually received a 10 card and decided to bet low. Again, these trials are associated in this case with a low internal state. So to try to bring the probability down. Now, what is, I think, even more interesting is when we look at the population. So here we can see that we have a spectrum of results. And so it's going from some patients like F316 on the top left that are very irrational. So essentially these patients often, I mean not often, but do sometimes bet high on the 2 and low on a 10. To our patients like F317 that are very, very rational and very static actually. So this patient, F317, is always betting the same way given the card. So always betting low for 2, 4, and 6, and always high on 8 and 10, except once, I think. And so, of course, because there is no variability for that particular patient, I mean, the notion of having an internal state that would explain this variability doesn't make a lot of sense, right? But we will see that in the next slide that actually our internal state goes to 0 for this patient. And then we have a third type of patient. So we have a patient like F36 on the bottom left, where essentially this patient is very rational on 2, 4, 8, and 10, so always betting low or high. But on the 6th card, he changes his behavior. And the model is able to capture this change of behavior by nicely separating the blue dots and the red dots with these internal states. So we can have a look at the trajectories, and we see that for the 2 type of patient like F316 or F36, so where we have variability on all cards or variability only on the 6th card, we have a nice internal state that is modulating, showing some fluctuations around 0. While for F316, where there is no variability on the data, in the data, essentially the state is just hovering close to 0. Okay. Okay, now the last step, once we have understood, at least we think that we have understood how the patient behave and make their decision, is to try to identify where are the different signals that we included in the model in the brain. And so, as a first warning, I would like to emphasize that I will show you figure like the one on the right. But these are not fMRI images. This is just a way that we use to represent our results. But the results that I will show you is results using stereotactic EEG data. Okay, so the way we analyze the neural data is very simple. So we have we have a channel coming from the electrodes, and we can take snapshots for each trial. We can take a snapshot of the data. And we can time lock all these snapshots to a particular epoch in the game. So it could be the show card epoch, the show bet epoch, the show computer card or show deck, and the show reward. And then we try to, and then we compute the spectrogram for each of these snapshots. So essentially, we just have a large pile of spectrogram. And let's say that we are interested in trying to see if we have some neural signal that is modulating with the card value. Then we can divide all the spectrograms into two piles. We can, for example, have a low card pile and a high card pile. And then we have some machinery that we took from the literature and that we adapted from the literature that allow us to go through these two piles and identify a cluster, which is just a region in the time frequency domain, where the spectrograms are showing a statistical significant difference. Okay? So now I'd like to show you a few results, and then I'll give you a kind of a more general view of all the different regions that activate with this task. So this is the first result where the behavioral signal that we are interested in is the expected outcome. So this notion of return that is in the output equation. And we identify that we see neural signal in lingula gyrus, which is a region in the occipital lobe that seems to have this cluster that is highlighted in red that shows some modulation with the expected outcome. And actually, if we compute the average, so for each trial, if we compute the average power that is in this cluster, and if we report that average power as a function of the card value, so you get the plot on the bottom right, and you see that the average power increase as a function of the card value. And actually, that's exactly what you expect when you are looking for the expected outcome, because the expected outcome is just a linear function of the card value. Okay, so lingula was interesting because it's a visual area. It's also related to memory, so to store this information that can be retrieved later in the task. And also in the literature, it has been associated to verbalization of high emotional words. So that, I mean, even though the modality is different, it might be something that is related to maybe associating different emotional value to different cards in the gambling task. Then the second type of behavioral variable that we were interested in is the variance of the outcome. And in this case, we found some neural signal in cuneus, which is also a visual area in the occipital lobe. And in this case, I mean, the frequency range of the cluster is different, but again, it's a nice cluster after the show card epoch. And again, if you compute the average power within that cluster, you plot that as a function of the card value. Now, this time, you get a very nice bell shape, which is exactly the shape of the variance of the outcome as a function of the card value. And interestingly, cuneus has been shown in the literature to be involved in pathological gamblers. So you have a higher activity in fMRI studies in cuneus for pathological gamblers. And it's also thought to be associated to go, no-go task. And maybe the relationship with our task with respect to that is that, I mean, the variance of the outcome is higher for the sixth card than the other. And so the sixth card is really the trials where the patient has to maybe think harder in order to process the emotion. So that might be the relationship with the go, no-go task. And then last but not least, then we were also looking for neural signal that modulate with the internal state that we estimated using our model. And we found some activity in amygdala, which is a region that is very well known for emotion processing. In this case, I'm showing you a cluster at the show reward. So that's when we show the picture of money. And again, it's a high-frequency cluster. And you see that we have, again, this increase in the average power when we report that for different low, medium, or high internal state. Okay, now I'd like to give you maybe a bigger picture. These were just 3 snapshots of the results that we have. Here I'm showing you the different columns are different epoch in the game. So you have show card, go queue, show deck, and then show reward. Different rows are just different view of the same brain. And then I'm highlighting in different colors different type of signals. So in blue, I'm highlighting the cognitive input. So it could be the expected outcome, variance of the outcome. In red, I'm highlighting all the regions that modulate with this internal state, and in orange, I'm showing you the overlap. And what is interesting is that for the cognitive input, we kind of see a flow from occipital regions that are visual regions toward more the front of the brain, going through memory first, and then maybe regions that are involved in this emotional processing. The interpretation for the emotion, for the internal states, is a little bit trickier. We are still in the process of trying to really understand exactly the flow of information. But we also see what is interesting and encouraging is that we see regions that are known to be involved in emotion processing that show some modulation. So we have amygdala, orbitofrontal cortex. We have also regions in the prefrontal cortex that are activated. So that's very encouraging to us. So I hope that I convince you that we have quite a unique data set, both in terms of neural data that we collect, but also in terms of the task, because there are very few tasks actually in the decision-making world that have pretty much 20% of the trials where you have no right decision. So something else than just expected reward must be driving your decision. And then I show you how we can use modeling in order to first understand the behavior, and then how we can explore a huge neural data set using the knowledge gained from the modeling. So the next time you face a tough decision, I hope that you will let your emotion modulate whatever the cognition is telling you to do. Thank you very much.
Okay, I think we can take one question.
I had a little bit of trouble, understanding. I understand bias versus its role in your experiments, but most quite get how that.
Yeah. So when we think about internal biases, it can be linked to different things. It could be just static internal preference. In general, you prefer blue to red. But it could also be some internal biases that are evolving. And as you mentioned when I asked the question, you say maybe it depends on how I perform on my last 6-card trial. And so that's and we call it internal bias in general because we didn't really ask the patient how they felt and things like that. But we think that this notion of internal biases is related to the emotion, because the ingredients that we put in the state evolution, and we put them there because we thought of them as they might be influencing the emotion. How you perform might influence your emotion, and also the notion of luck, which card you receive might influence your emotion. So, but to be on the safe side, we just call it internal bias.
Okay, so let's.
I just want to congratulate an unfair bet for the 6 especially, where that decision is interesting, where people sometimes will flip. If you actually do tell them that, but you frame it so that this thing would actually control the 6, you're more likely to go high and low, because they learn that somehow through their emotional state.
Yeah, so that's definitely something that we would like to do. So we would like to do 2 main things in the future. First, try to rig the deck, to try to influence their decision, and even on the fly, maybe track their decision and try to tweak, which card is coming up to try to drive the player in different emotional state or different internal bias states. So that's something that we think of doing. And then another thing that we are maybe thinking of doing is to try to stimulate, because they have these electrodes, and so with these electrodes we can also stimulate and see if we identify a region that is clearly biasing the player, and that show high activity when the player is biased toward high bet. Then can we activate and stimulate these regions to force the player to bet high, for example? So these are the 2 main things that we have in mind for the future.
Okay, so let's thank our speaker again for this session.